Welcome to This Explainer. Let's just dive right in and demystify the mechanical magic of the steam engine. For over a century, this technology absolutely ruled the world, powering the factories and locomotives that literally drove the Industrial Revolution. Today, we're going to look closely at the brilliant engineering that fundamentally changed how we humans harness power. I mean, think about it for a second. It is the ultimate physical problem. How do you harness simple heat and turn it into massive mechanical motion? How exactly does a cloud of vapor, which seems so incredibly light and formless to us, manage to move a literal mountain of steel, like a massive locomotive hauling thousands of tons? Well, the answer lies in mastering some fundamental thermodynamics and applying some incredibly clever mechanical linkages. Part 1. Turning heat into motion. So the crucial point here is that the entire purpose of this machine is to translate a simple back-and-forth push into a continuous circular drive. Heat energy from high-pressure steam gets converted into mechanical energy, right? But a simple back-and-forth, or reciprocatory, motion just isn't enough on its own to drive a heavy train wheel down a track. To actually do useful continuous mechanical work, that raw linear energy has to be smoothly transitioned into a rotatory or circular motion. Part 2. The boiler and piston. Now consider how these two simple repeating thermodynamic steps generate that essential reciprocatory motion we were just talking about. Inside the cylinder block, steam acts on a heavy disc-shaped piston. During the expansion mode, heat adds intense kinetic energy to the gas particles, basically making them bounce furiously against the cylinder walls. This highly pressurized gas naturally wants to expand, so it pushes the piston forcefully outward. Then, in the compression mode, the gas compresses, moving the piston back inward. This relentless, alternating to and fro rhythm, that becomes the literal beating heart of the engine. And this creates a perfect kinetic chain reaction. First, the boiler generates the high-pressure steam and feeds it directly to the cylinder. As the steam acts on the piston, the heavy piston rod drives forward, thrusting a sliding, heavy-duty guide piece called the crosshead. That immense forward thrust of the crosshead transmits the raw force to the main connecting rod, which, finally, turns the crank and the crankshaft. It's an absolutely flawless kinetic sequence, reliably transferring power step by step from a cloud of hot vapor directly to the driving wheel. Part 3. Directing flow. Slide valves. But a cylinder is entirely useless without a brain to direct it. It basically needs a traffic controller. If we want to visualize this invisible steam pressure as we discuss how these valves work, think about a color scale. Red represents the most powerful, high-pressure steam entering directly from the throttle. Magenta shows the steam as it's actively expanding inside the cylinder. Blue is the used exhaust steam venting out to the smokestack and the atmosphere, while green represents the remaining exhaust in the cylinder being compressed. The precise timing of when these different states enter and exit the cylinder, that is completely managed by the valve. Historically, this traffic control was handled by slide valves, kind of like the famous D-slide valve invented by William Murdoch way back in 1799. And it worked wonderfully for 19th century engines. But as engineers pushed for far more power using superheated steam, slide valves became notoriously difficult to maintain. The intense heat would literally burn off standard lubricating oils, causing immense friction. Because of this, the industry transitioned to piston valves. These allowed for much shorter steam passages, which drastically reduced flow resistance and, ultimately, improved the engine's overall efficiency and reliability, a real game changer. Part 4. Controlling speed. The governor. Just think about this beautifully simple, absolutely ingenious mechanism. This is the classical brass flyball governor, implemented by James Watt back in 1787. The central spindle is directly connected to the shaft of the engine. As the engine speeds up, centrifugal force takes over and pushes those heavy brass flyballs upward and outward. Through a brilliant series of mechanical arms, this upward movement physically closes the throttle valve, reducing the steam input and automatically slowing the engine down. It's essentially an early mechanical cruise control. Now, this feedbackward loop is brilliant because it actively seeks equilibrium. But there's a fascinating catch in the physics here. If the mechanical gain is too large, meaning if the flyballs influence the throttle too aggressively, the engine will suffer from wildly unstable oscillating speeds. In physics, this complete loss of stability and creation of a constant erratic oscillation is known as a Hopf bifurcation. The engine literally starts hunting for a stable speed, surging violently up and down rather than running smoothly. And what's wild is that this physics concept is so fundamental, the exact same feedback loop can be recreated today using basic Lego bricks. By using a Lego rotation sensor to measure the angle of the arms and a programmatic brick to regulate power to an electric motor, modern students can witness the exact same mechanical stabilization in action. And actually, if the software parameters are set too aggressively, they can witness that exact same Hopf bifurcation we just talked about. So it leaves us with a really profound and fascinating thought to take away. How did solving the gritty mechanical problems of the 18th century steam engine directly inspire the automated robotic world we live in today? Every single time an autonomous drone automatically stabilizes itself in the wind, or your home thermostat quietly clicks off when it reaches the perfect temperature, it owes a direct technological debt to James Watt, a spinning set of brass balls, and the relentless quest to perfectly control a simple cloud of vapor. Thank you so much for joining me on this explainer. I hope this structural breakdown helped you grasp just how elegant heavy machinery can truly be.